Hey everybody, this is Mr. Clapp explaining several lines of evidence that the Earth rotates. If you want to see evidence that the Earth is round, check out our other video. If you want to see evidence that the Earth revolves around the sun, we'll talk about that soon. But that said, let's actually make sure we understand these different terms. So rotation means spinning on an axis. So the Earth spinning around like it is in this GIF is a rotating Earth. And we know that it takes 24 hours for the Earth to rotate around once, or just about. We'll get to that later. But again, the Earth rotates pretty much once every day. Revolution is a different concept. Revolution means that the Earth revolves around something else. And of course, in our case, it revolves around the sun. We also know the Earth is revolving, but that's not the subject of this PowerPoint. The focus of our discussion is a rotating Earth, not a revolving Earth. We'll get to that later. So let's talk about some of the terms we use when we talk about rotation. When we talk about rotation, we often talk about the axis of rotation. So imagine the Earth is a rotisserie chicken, right? If the Earth is a rotisserie chicken, that spit of the rotisserie chicken, that's the axis of rotation. It's what the rotation goes around. Now the Earth, of course, doesn't have a stick sticking through it, but it still has that axis of rotation. As we spin around, you can imagine this axis pointing straight up from the North Pole, actually to the North Star, and straight out from the South Pole out into the abyss. So again, we have the axis that we spin around. This is our axis of rotation. So before we get to the lines of evidence that we're rotating, we need to be honest about some things. First of all, there's a big claim here, and it's not supported by our everyday observations, or some of our everyday observations. The first question we have to ask is, are you moving right now? According to what we're saying, the Earth is spinning really, really fast, and you are too, unless you're standing on the North or South Pole. So here's the claim, right? We're claiming that someone on the equator has to make it the entire way around the Earth in a 24-hour period. That's a distance of 40,000 kilometers, which means they have to be going about 1,600 kilometers an hour. That's pretty darn fast. Someone at the pole doesn't move nearly as fast. Matter of fact, in a 24-hour period, they would just spin around in a circle and wouldn't move at all. So they don't move much. But down at the equator, we move a lot. And in between, we still move a good bit. Since we in Reno here are about halfway from the equator to the North Pole, this kid, eating his fire-hot Cheetos or popcorn or whatever he is, drinking his soda and watching TV, is moving at about 500 miles an hour or 800 kilometers an hour. That's amazing. He's moving incredibly fast. To put it in perspective, Usain Bolt only moves about 36 kilometers per hour, far less than this kid does. And heck, even a really fast car like this Bugatti here, the fastest it can go is about 464 kilometers an hour. That's fast. Someone hanging out at a latitude of about 38 degrees, like here in Reno or in San Francisco, someone there is moving about twice as fast as this Bugatti can go at its top speed. Someone at the equator, 4 times as fast. So we're moving, and we're moving really, really fast. But that's a pretty big claim. We're claiming that if this Bugatti is at the North Pole and the kid is at the equator, that he's moving 4 times as fast. Now, I know for you, I certainly don't feel like I'm moving when I'm sitting on a couch. But this car, it would feel like I'm moving in the car. So this is a pretty audacious claim, and it's not very parsimonious. It doesn't seem to make sense from our perspective. It sure doesn't feel like we're rotating. Items don't go flying off our desk like they would if I held them out the Bugatti. And things don't go flying around like they would if I spun around on a merry-go-round. If we're spinning, and additionally, why don't objects that are fired east travel faster than ones fired west? If I shoot a cannon to the east, it should take advantage of that Earth's spin and go a lot faster than one going the other direction. But none of these things are observed. And so this draws us, we have to be honest about our assessment here. Some of this doesn't feel right. It doesn't feel very parsimonious to say we're not rotating if it doesn't feel like it. So this gives us a big challenge, right? We have to present enough evidence that we're rotating to counteract this feeling that we're not. It doesn't feel like we're rotating, and it just doesn't look like it from a daily basis. So our evidence has to be really strong. In the end, it still needs to be simpler of an explanation to have us rotating without feeling like it than we're sitting still. So that's a pretty high bar. Let's see how we do. Okay, so we're going to present 6 different lines of evidence Some of them are strong, some of them have some flaws to them, but they all give us something to lean on when we talk about the Earth's rotation. And we're going to start with time zones. So as you hopefully know, if you go around the Earth, we have different time zones. I'm sitting here in Reno, Nevada. It's about 10 o'clock p.m. for me here. And that means in New York City, it's about 3 hours ahead of that for them. So it's 1 a.m. in the morning. If you go all the way back to England, it's another 3 or 4 hours for them. So they're going to be at 5 in the morning. And you keep working your way on back. All around the world, we're experiencing different times at the same time. So again, according to this map, say it's noon on the prime meridian, it's going to be almost midnight if you're all the way over in the Aleutian Islands off of Anchorage. So we all experience noon and other times at different moments during the actual day. For example, again, if you're in New York City, say it's 2 p.m. for you and the sun has just passed transit a couple hours ago. Well, someone in Chicago at the same time might be experiencing noon at the same time. Their sun is transiting. Whereas someone in San Francisco, the sun hasn't transited yet. And forgive me, I'm playing with these time zones a little bit, but you get the idea. Different people at the exact same moment in time experience the sun in different spots. So all three of these events happen at exactly the same time. And this is why we have time zones. I want noon for me to be pretty darn close to when the sun goes and transits for me. It doesn't help that it transited 3 hours ago in New York. And this is why we have time zones, to set that up. There are two very simple competing ways we can explain time zones. One way to explain it is that the sun is moving across the sky. From our perspective, this is sure what it feels like, that we're sitting still and the sun passes from east to west through our sky. This would make sense, and this would be one explanation. But one of these two things is happening. Either the sun is moving through our sky, or the sun is relatively stationary and we're actually spinning. Either one of these explanations works, but we have to be honest about the fact that one of those two things must be happening. Either the sun is moving or we are. Again, because of relative motion, we can't tell whether the sun's moving or we are. So either explanation works. We have to move on, but we do know that at least the sun is moving or we are. So let's go to another one that has a really similar feel to it. The stars also appear to move. If you look up in the sky, and these are these great star trail photos that you can see by looking up in the sky. This one pictured on the left is looking north. Looks like it's from Bodie, California. And from here, you can see pretty darn close to the North Star. And you can see that over time, the stars are spinning. The way these photos are taken is the artist opens the aperture to the camera and leaves it open for a while. And what happens is you can actually see the motion of the stars as they spin around. So you can see this rotation of the sky that happens throughout any night. Stars appear to move. There's no question about it. Anybody who spent any time looking at the stars at night, notice they rotate at a rate of about 15 degrees per hour in a 360-degree circle. Stars in the northern hemisphere rotate counterclockwise. Stars in the southern hemisphere rotate clockwise, but they all rotate. Here's a couple of quick videos. So here's some star motion looking west or in the northern hemisphere, and you can see the stars appear to be setting off to the west and circling around a North Star that's off to the right. Again, this is just a sped up time lapse of an evening. There's no trickery here. It's just a relatively quick moving sky. And there's the beautiful view that you would get if you had the star trails motion instead. Here's the same sky looking to the east. Again, to the east, it comes up and wraps around the north, which is now off to our left. Again, same perspective, same thing. And again, here's that beautiful star trail where they left their aperture open and get that same perspective for us. Finally, here we are looking to the north. And if you look to the north, you see that central star Polaris right there in the middle. And we see the rest of the sky spinning around it counterclockwise, like we've already talked about. The sky appears to move. There's really no question about this. Everybody can observe this. All you have to do is go out at night for a couple of hours and you'll see it. So here we are in the southern hemisphere and we see the same thing. Our star trails are still apparent, but they're going the opposite way. So here we are looking west and we see the stars set in a very similar fashion, but spinning around something to the left as opposed to something to the right. This is a nice star party. You can see all the scopes down here. There's the star trails spinning around the south celestial pole down to the left. Same idea, looking east. We still see the stars appear to rise here, but they're spinning around what looks like a southern spot as opposed to a northern spot. And here we are looking now south to the celestial pole, and down here we see the sky rotating around a central point. No good North Star here, but we can still see that rotation. The rotation is going clockwise instead of counterclockwise. But again, still a very obvious rotating sky. So we see stars rotate around the North Star. There's no question about this. If you're facing south, like we said before, we see stars rotate the opposite direction around a south point. We also see the sun rise in the east, transit in the south, and set in the west. We see this every day. Both of these things are observable things that we just notice are happening. Now, there are a couple of explanations for this. Again, either the sky is spinning, or the sun is moving across the sky, or we're moving. We talked a little bit about time zones and the fact that we see the sun moving here, and that really makes sense in that context. The fact that we see the sky moving means it has to be something more than just the sun moving through the sky. It has to be either the stars also moving or we're spinning. Relative motion again, this explains why either one of these would work. Either the Earth is spinning to the left or the sun is moving to the right. Either explanation works. So either the Earth is spinning or the stars are. And it's often a useful tool to think of the stars as fixed objects attached to a giant sphere that spins around the Earth. Many traditional stories have the sky filled with holes, but the sky is all at one distance. This could work, but we know now that stars aren't like this. Stars are suns just like our own that are separated by great distances. They're not attached to a big blanket that stretches around the Earth. The stars aren't actually fixed. They're on their own, and they're out there moving around. If the celestial sphere is spinning and every star is actually moving, they all have to move at exactly the right speed so they look like they're all spinning together. This doesn't make a ton of sense, and it's not terribly parsimonious. I'll give you an example. This constellation of Taurus, or this section of the constellation of Taurus, is really observable in the winter sky. It's made up of a very, very bright star called Aldebaran, which happens to be about 65 light years away. And then the rest of the stars that make up this V are what are called the Hyades, the half-sisters of the Pleiades in ancient Greek stories. They are about twice as to 3 times as far away as Aldebaran. Yet, when we look up in the sky, these things appear to move the same. They move across the sky at the same rate. We don't see any relative change in where Aldebaran is relative to the rest of the Hyades. Well, this only makes sense if the Earth is stationary and Aldebaran is moving slow and the Hyades are moving much, much faster, just to make it look like we see them all moving at the same time. This doesn't make a ton of sense. That's what would have to happen with every star in the heavens for us in order for a spinning sky to make sense. So again, either explanation works, a spinning Earth or a spinning sky, but it's crazy to think that every star is spinning at exactly the rate so it looks like they're not moving faster or slower to us here on Earth. So, what does that mean? Well, it means the Earth is likely spinning. It's the parsimonious explanation. It's important to think about not only the time it takes to spin, but also the direction it's spinning. The Earth is spinning to the east, which is why we see the sun as we kind of dive to the east as it rises. And as the Earth catches up with it in the west, that's how it sets. Our next line of evidence for a rotating Earth gets away from all of these, well, either the Earth is spinning or the sky and spinning sun is moving. These are only explained by a spinning Earth. And they get a little complicated, but we're going to go ahead and give it a shot. Imagine this girl in a car holding her teddy bear out the window. Let's say the car is going 100 kilometers an hour, 62 kilometers an hour along the freeway. Well, she's moving that speed, the car's moving that speed, and so is the teddy bear. Well, imagine she lets go of the teddy bear. If she lets go of the bear, it's going to continue moving at 100 kilometers per hour for a little bit until the air hitting it slows it down, or hitting the ground, it slows down due to friction. But for some time, it maintains its speed. That's what inertia is, the tendency to keep doing what you're doing. This also happens on the Earth. The Earth spins once a day, but this doesn't mean the entirety of the Earth goes the same distance. Air near the equator has to go all the way around 40,000 kilometers in 24 hours. As you move towards the poles, like we mentioned before, you don't have to move as much. So you actually move slower if you're air towards either of the poles. Air and water keep the speed where they start moving. And if they move off of the equator or towards the equator, they're going to feel that relative fast school, slow school kind of situation we talked about before. The result of this is a swirling of air. And air, you can actually see several hurricanes or cyclones in this picture. And these are swirlings of air that we get because of this effect. In the northern hemisphere, we get this swirling of air where they go to the right or counterclockwise. In the southern hemisphere, they move clockwise. But these swirlings of air are explained by what we call the Coriolis effect. And here's a couple videos, again, one in the northern hemisphere, one in the southern. In the northern hemisphere, you see that they're rotating counterclockwise as it goes towards Florida. And here near Australia, up in Queensland, you'll see it's rotating the opposite direction. So what explains this? Again, it's this rotating of the planet where air has different speeds. This video to me explains it pretty well, although a little fast for me, but go ahead and check it out.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you, but if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low-pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise, and that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving this example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video, and that's kind of the point. I hope you got what you came for. And the Coriolis effect doesn't really influence toilets, they're just really too small, and the direction of the spin more depends on the placements of jets inside the toilet. But that's it, that's the Coriolis effect.
So again, I think a solid explanation of the Coriolis effect, which only is explained by a rotating Earth. This video explains how the Coriolis effect can show up when you're firing a rifle a really long distance. I think it's a really neat effect, and this guy explains it well. He uses some languages that are typical for guns that you may not understand otherwise, but go ahead and give it a listen and we'll explain stuff as we need to.
Hi, I'm Jeremy Winters, product specialist here at Gunworks. Today we're going to go over one of the common issues guys have when collecting data to either build a drop chart or a ballistic compensator like we use on our systems. We field hundreds of calls a month where guys cannot re-verify their data once they've shot it one day and go out and try to return the same data, let's say a week later. And one of the common issues that we see is the Coriolis effect. And what guys are not doing is taking into account the effect that this can have on your shooting at longer ranges. Now, real quick, let's kind of just explain the Coriolis effect in layman's terms. The Coriolis effect is the effect that when the bullet leaves the barrel of the gun, it is actually leaving the surface of the earth. So as the bullet leaves the barrel of the gun, the earth is still rotating and the bullet is not rotating with the earth. So the earth will actually rotate out from underneath of the bullet while it is in flight. So as the Earth rotates, it actually rotates from the west to the east. So what that's going to do to our targets is if you're shooting west, your target's going to rotate up and towards us, which is going to cause the bullets to hit lower. And if you're facing east, the target's going to be dropping and slightly moving away, which is going to cause the hits to be higher. Now, why this is important is out to 1,000 yards, you could have almost a full minute of correction due to...
When he talks about a minute here, he actually means an arc minute. We've talked about this a while ago. It's a fraction of a degree. Degrees are broken down into 60 minutes, and that's what he means when he's talking about a minute. You're going to have that much air because of the Coriolis effect when shooting these different directions.
Coriolis effect, depending on which direction you sighted in your zero. Now, to show you guys just how much effect there's going to be, we're going to put on a little shooting demonstration here. I've got targets east or west and east of us, exactly 1,000 yards in each direction. So what we're going to do to prove this Coriolis effect on our rifle here is we're going to shoot it out to 1,000 to the west, and we're going to shoot it to 1,000 to the east, and we're going to measure the difference in those group centers. And hopefully it's going to show you guys that this kind of error can lead to bigger errors in your drop data. All right, got 3 hits on the steel down there. We're gonna switch directions, switch the bents over, and we're gonna shoot east now. All right, we got 3 more hits on this steel down here. Now we're gonna rack up all our gear. We're gonna go check these out, measure them up, show you the results. All right, we've made it down to our target that we shot at the west. This is our west target here. And as you can see, they've all dropped in quite low. We've got 8 inches from center to the center of the group, which is a little lower than we expected, but we were dealing with some pretty stiff mirage. So we got a nice little group here. We're gonna pack up this target and head down to our target that we shot to the east, and we'll compare the 2 groups and show you the difference of just switching directions. That's all we did. We switched from west to east. All right, we've made it down to our target on the east target now. And as you can see, they're not quite too high. We've got about 3 inches, maybe 3.5 to the center of the group above bullseye. So if we compare this to our other target, we're 3 inches high here, we're 8 inches low there. That's 11 inches, just over a minute of difference between just shooting from the west to the east.
So a pretty crazy effect for sure. And again, demonstrable, something you could do here in Nevada if you wanted to and had the access to those resources. So pretty neat stuff, Coriolis effect and the effect on bullets. Okay, let's move on to yet another line of evidence. This one's also really interesting because it's only explained by a rotating Earth. And it's called Foucault's pendulum. You may have seen these before. Leon Foucault in 1851 supposedly built the first one of these. And what it is it's a pendulum that swings on a frictionless pivot, so it's allowed to turn any direction. When you make one of these pendulums, as it goes back and forth, it appears to rotate around. And your latitude actually determines how fast it rotates. The farther north you are, the faster it'll go around in a circle. The closer you are to the equator, the less pronounced an effect you have. So what you'll see here is as this pendulum swings, it gets closer and closer to this peg. And over about a 30-hour period, it'll go all the way around and knock down every one of these pegs. And I'm going to go ahead and jump ahead just a little bit so we get closer to seeing it. But you'll notice it keeps getting closer and closer to that peg, and eventually it'll knock it down. Wait a few more minutes, and it'll knock the next one down. So again, the pendulum appears to be rotating, and it doesn't make sense why. Here's a similar video of a Foucault's pendulum shot over about a 30-hour time lapse. And again, you can watch it very quickly swinging back and forth and knocking down all of the pegs. So the pendulum appears to spin, but there's no force that can explain the spinning. Why do they appear to spin when they don't? It's not that the pendulum is spinning. The pendulum is staying and doing exactly what it normally does, moving back and forth. What's spinning? Let's let this professor explain to us what happens with a Foucault's pendulum.
Foucault pendulum is a pendulum with a specially designed pivot, designed so that it can swing back and forth in any direction around the vertical. So that's in contrast to, for example, a grandfather clock, where the pendulum has to swing in a particular plane. Let's imagine that you have a Foucault pendulum and you're at the North Pole of the Earth. When you set the pendulum swinging, you determine a plane in which the pendulum is swinging. And that plane is fixed. So as the Earth rotates underneath the plane of the pendulum swinging. And so if you now go back and imagine that you're standing on the Earth, you see the plane of the pendulum rotate every 24 hours. Now as you go to lower latitudes away from the North Pole, the time that it takes the plane of the pendulum to rotate around lengthens. And in fact, at the equator, the plane doesn't rotate at all. At the latitude of Hanover, it takes 35 hours for the plane to rotate. So if you look at this pendulum here, if we look at it a few minutes from now, we won't even be able to detect that the plane of the pendulum swing has changed. But if you come back in an hour, you will definitely see that it's moved a little bit. And if you come back in 9 hours, this plane of this pendulum here will have rotated by 90 degrees, a very distinct change that you can easily see. Plane of the pendulum swing is also affected, for example, by the revolution of the Earth around the sun. And so, for example, if you have a Foucault pendulum at the North Pole of the Earth, not only will it rotate around every day because the Earth is rotating, but you will also get a much longer rotation over the period of a year from the revolution of the Earth around the sun. So if you think about it, this Foucault pendulum here is a kind of rotation meter. It's a way of measuring rotations. A suitably placed Foucault pendulum can be used to detect the rotation of the Earth or the revolution of the Earth around the sun, or in principle, you could use a suitably oriented Foucault pendulum to measure the rotation, for example, of the solar system around the galaxy. So this brings up the question. The Foucault pendulum is sensitive to rotation, but rotation around what? And there's been a lot of speculation in physics and philosophy about that question. Ernst Mach, a 19th and 20th century physicist, put forward the conjecture that the Foucault pendulum is measuring rotation relative to the universe as a whole. Makes a kind of interesting connection between a local physics experiment here in this room and the universe as a whole. And the problem that people bring up is, how can this pendulum here somehow know something about the entire universe? So it remains as an unproven conjecture, more in the realm of philosophy than in physics at this point.
So yes, a fascinating explanation from clearly a brilliant mind. Okay, so Foucault's pendulum measures the rotation of the Earth. The pendulum keeps going, and the Earth spins out beneath it. It looks to us like it's rotating, but in fact, it's us that's rotating. Okay, 2 more. We'll get through these ones kind of quick. Other objects in our solar system appear to rotate. When we talked about evidence that the Earth was round, we talked about how other objects in our solar system are also round. And parsimoniously, it makes sense that we are as well. When we look at objects in our solar system, they all appear to rotate. Here's a time-lapse rotation of Mars. Here's a time-lapse rotation of Venus, again, spinning around over a period of hours. And here's a time-lapse rotation of Jupiter. Jupiter, in fact, is rotating really, really quickly. Despite its size, it takes only about 10 hours for it to rotate. The giant red spot on Jupiter and all these other storms have really strong Coriolis effects, which we can see with high-powered telescopes. So, if everybody else is rotating, why aren't we? It would make sense that we are as well. Incidentally, there's one object that kind of rotates, but it's a little confusing. When you look at the moon, you got to ask yourself, we always see the same face of the moon. The side we see here is pictured on the left, the side we don't see on the right. So is the moon rotating? If we always see the same side, doesn't that mean it's not? Well, in fact, it means it is rotating, because the only way we can see the same side is if that side always works to face us. Imagine standing in the center of a room and having someone walk around you in a circle. The only way you would see their same face is if they rotated around so that their face was always facing towards you and not towards some other distant object. So the period of rotation of the moon and the period of revolution are actually the same. It takes the moon 28 days or so to get around, and it takes 28 or so days to actually rotate. This is what we call tidally locked, and this is true for many small objects around large ones. Our moon is tidally locked to us. The moons of Jupiter are tidally locked to it. Mercury is tidally locked to the sun, and this happens to objects. But nevertheless, they are rotating just once per revolution. Okay, our final line of evidence is one that may be a little hard to explain without other context, but if you're interested, we can talk about tides in more detail. But tides are also evidence of a rotating Earth. When you look at the tides in areas where the ocean meets the land, we see these really pronounced differences from one time of day to another. This picture here is taken in Seal Cove in the Bay of Fundy, and you'll notice that the tide goes way, way in and way, way out. The Bay of Fundy has the most pronounced tides in the world, but everywhere in the world you get a similar effect, where water rushes in and water rushes out. It happens twice a day, such that every day you have 2 high tides and 2 low tides. Again, pictured here, sort of a high and then a low. So every 24 hours, you get 2 of those. So why do we get this? Well, again, tides are the daily rise and fall of the oceans. Though tides are more pronounced in some areas than others, all oceans experience tides. Again, 2 highs and 2 lows. Why do we get these? Generally, tides are caused by the gravity of the sun and the moon. These bulges of water, which are exaggerated on this picture of the kind of teal earth here, are pulled by the moon and the sun. Since the moon is much closer, it has a strong pull, the sun less of a pull. But they're called by the gravity of the moon and the sun. Though the moon revolves around the earth once every 28 days, the earth spins really fast. So effectively, the moon stays in the same spot for one of our rotations. But what happens is we actually rotate into a bulge that faces the moon. The earth spins, the bulge stays in the same spot, and the end effect is we move into this bulge of water, resulting in a high tide, and then move away from it, resulting in lower tides. So we literally experience a stationary tide, relatively, and a spinning earth. We spin in and out of high and low tides twice a day. Neil deGrasse Tyson explains this a little bit better than I do, so let me give you another 4-minute explanation of his, and then we'll call it a day.
From my personal experience, anything you want to know, this man right here, especially when it comes to science, has the answer. Okay? So.
No, I have an answer. Whether or not it's the answer, that's to be determined.
Please, you're ruining what I believe in. Okay?
I want to dismantle your belief system.
Yes, exactly. My whole world is crumbling. I need to believe in you, man. All right?
Tides are widely misunderstood.
Okay.
All right? I will say, the next thing I say may be mind-blowing to you.
Okay.
Okay? The tide doesn't actually come in and out. What? What happens is there is a bulge of water, 2 of them, on opposite sides of the Earth, caused by the sun and the moon, and Earth turns inside that bulge. Mm-hmm. So when we say the water rises and falls tidally, what's happening is we are rotating into the bulge and then out of the bulge.
So the bulge is already there.
It's already there.
And all we kind of do is pass through the bulge.
Pass through, and the water gets high and it gets low. So we're stuck with language from our own perspective rather than language of what's actually happening. It's simpler that way to say the water goes in and out. It's simpler to say the sun set rather than Earth rotated such that our angle of view on the stationary sun fell below our local horizon.
Right.
Yeah,
sunset is far more poetic.
Yeah, you go to the sunset tables, to look this up.
Yeah, because you can't say to a girl, hey, how'd you like to go and watch the angular momentum of the Earth cause the sun to disappear behind a horizon?
Hello, where'd you go?
And Dr. Tyson's explanation goes on, but for our purposes, this explanation of the two bulges is good enough. The Earth rotates in and out of those tidal bulges. And there you have it, 6 lines of evidence that the Earth is rotating. Hopefully that helps. And if you have any other questions, feel free to ask, leave comments, or talk to me later.